Let's get this set up. All right. Switch this over. Oh, sorry. Okay. Hammy, no, be good. All right, guys, sorry about the late start. Had a bit of a crazy morning. My cat got attacked last night, and I had to run her to the vet. But today is our review day for the test, and since we're starting about 10 minutes late, I'll make sure that we go about 10 minutes over to make up for that. Hopefully you guys have lots of questions you want to talk about, problems from homework, problems from the study guide, wherever you would like to get them. I'm happy to solve them today. So let's get to it. Where would we like to begin? Feel free to type in the chat, just letting me know which problems you would like to look at. Yeah, I think she's going to be okay. This cat's just like a magnet for trouble in the last few weeks. But something bit her. She had a just straight up hole on her side. But she's going to be okay. We rushed her to the Millhopper vet this morning, and they already called us back saying we're going to start her on some IV antibiotics. Take a look, make sure her lungs aren't punctured. So hopefully she'll be okay. I have faith she will be. Okay. So yeah, just like you see Damon there, go ahead and let me know which problems you guys would like to work. They are good, yeah. Last time she got hurt, we took her to the, last time she got hurt, we took her to the UF Small Animal Hospital, and I've had them do things for me in the past, but they did not do nearly as good a job as Millhopper had done in the past, so we're going back to them for this. Looks like number 25 from homework 5 is popular, so we will kick off with that. From 5. Okay. Yeah, 22 is a really good problem. 25 is also a good problem. Okay. I think 22 is a better problem to start with. Conceptually, this is an excellent question. This would make a very good exam problem. So let's make sure that we're all super duper comfy with it. Pencil works. Actually, I'm sorry. Give me just 1 second to find a better writing implement. There we go. Good. No. Oh. So for number 22 here, which is where we're going to start, say, of course, is the 17? Yeah. Today we're just going to do the review for the exam, and we're going to start with question number 22. They give you these graphs here, and I don't want to waste time drawing them myself, so let's try something like this. So you can see the graphs over there on the left, and you can see my dot cam over here on the right. We're told that U is F times G. Oh, this pen is dying. And V is F over G. And we're asked to calculate a couple of derivatives. We want to find U primed of 1, that's the derivative of U, evaluated at x equals 1, and V primed of 5, that's the derivative of V, evaluated at x equals 5. I saw something here. So anybody got any ideas how we could get started? For part A, say, if I wanted to find u primed of 1, I need u primed of x, right? I need the derivative. I need that as a function. And then I'm going to plug in 1. So here we want to find remember, u primed of 1 is the derivative function u primed of x with x equals 1 plugged in. So to do this, we need u primed of x. Challenge, of course, being I don't have a formula for the function u. All I know is that it's f times g. And when it comes to f and g, I have graphs, not algebraic expressions. But we can do the computation symbolically. U primed of x, it's the derivative of u, and u is f times g. So this is f of x times g of x, all primed. And I don't know about you, but that looks like a product rule thing to me, right? F times g, that's definitely a product. So if I want to prime the product function, f of x times g of x, I prime f, and I leave g alone. And then I add that to what I get when I leave f alone, but prime g. And again, I don't have an explicit formula for this. But I'm not after an explicit formula. I'm after a particular number, u primed of 1. So u primed of 1 is going to be, I'm just going to plug in 1 in this formula. It's f primed of 1 times g of 1 plus f of 1 times g primed of 1. And each of those things, those 4 things I need, I can get from the graph. So if we look over here on our graph, we can say g of 1. Let's go after that first. So I'm going to go after g of 1 and f of 1, and then f primed and g primed of 1. G of 1, if I'm looking on this graph and seeing correctly here, where's my x-axis? My horizontal axis, my x-axis is right here. X equals 1 is right here. So g of 1 is 1. That's the y value on the graph, on the blue graph right there above x equals 1. And f of 1 is 2. So g of 1 from the graph is 1. F of 1 from the graph is 2. But we still need f primed of 1 and g primed of 1. Could somebody describe to me in words, what is f primed of 1? There's a nice succinct sentence here. Who could describe to me what f primed of 1 is in terms of that graph? Good. Yeah, Mary hit it right on the head. It's the slope of the graph, f, so the slope of the red graph, at x equals 1. So I look along here, x equals 1. Oh, okay, I go up here to 1 comma f of 1. The slope of the tangent line right there is going to be just the slope of the graph, because the graph for that section is linear. In fact, both f and g are piecewise linear. They're made out of straight line pieces. So if I'm looking for the slope of the tangent line right here, that is the slope of this whole line segment right here. All right, the tangent line, you can imagine sitting in there, would sit right on top of the function here. It would agree with the function everywhere right in here, because the function isn't curving, because it's a flat line, it's a straight line. So that slope, to me, appears to be, let's see, if I go over 1, I go up 2. So f primed of 1 is 2. And now we need to compute g primed of 1. And the same sort of thing. I look on the blue graph, I go to the point where x equals 1, and I find the slope. That to me appears to be -1. So u primed of 1 is 2 times 1 plus 2 times -1, which is 2 minus 2, that's 0. So u primed of 1 is 0. Now we don't have the graph of u, so I can't analyze the graph of u on its own. But I can tell you what u primed of 1 is by using the product rule and then grabbing each of those individual pieces from the graphs of f and g respectively. To get started on the second part, we're going to need the same sort of thing. Only this time we have to start with the quotient rule because the function v is defined to be f of x over g of x. So before I move on to the second part, any questions on this first part here? Okay. So now we need v primed of x. In order to get v primed of 5, we need v primed of x. But v primed of x is what you get when you differentiate v, and v is f over g. So that's f over g all primed. And then you've got your quotient rule. And the mnemonic there is low d high minus high d low over low low. In other words, this is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom all squared. And so the thing I want, v primed of 5, is what you get by plugging 5 in for x. So v primed of 5 should be g of 5 times f primed of 5 minus f of 5 times g primed of 5 all over g of 5 squared. So just like in the previous problem, I needed f of 1, f primed of 1, g of 1, g primed of 1. Here I need f and g and their derivatives evaluated at 5. So I look on my graph, okay, 1, 2, 3, 4, 5. Looks to me like g of 5 is that 2? And f of 5 is 3. So g of 5, this piece right here is 2. F of 5, this piece right here is 3. F primed of 5, that's the slope of the red graph at this point. Again, f is piecewise linear, so the slope of the tangent line there is just the slope of the graph. I've got 1, 2, 3, 4, 5. Yeah, so the slope of the red graph right here at x equals 5 looks to me to be -1/3. All right, if we go over 3, we're going down 1, right? My rise from here is -1, my run here is 3. And this piece definitely has the same slope as the function right at that point. So f primed of 5 is -1/3. Just looking at the slope. And g primed of 5, if I look right here, the slope of this guy, let's see, it looks like I've got from here, let's say, so about 1, 2, 3, 4, 5. Yeah, we're looking for the slope right here. I see a rise of 2 and a run of 3, right? Rise of 2 and a run of 3 for that line. So that's positive 2/3. And that's everything we need. G of 5 down here, we already found that. That's 2. So this guy see, I'm gonna have to zoom out a little bit. This guy is, oh, that won't fit there. Let's do it down here. This guy is g of 5, that's 2, times f prime of 5 was negative 1/3. So negative 1/3. See that? Minus f of 5 is 3, and g prime of 5 is positive 2/3. And all of this is being divided by g of 5 squared. And g of 5 was 2, so g of 5 squared is 2 squared. All right, so that's what my quotient rule looks like with everything plugged in. And now I just simplify a little bit. 2 times negative 1/3, that's negative 2/3. Minus 3 times positive 2/3, that's minus 2. All over 2 squared is 4. This is a 2/3. Negative coming from the 2 times 1/3. And then this minus is this minus coming from the formula. And 3 times negative 2/3, the 3's cancel, you just get negative 2. So we need to have a common denominator upstairs. 2 is the same as 6 over 3, so this is negative 2 over 3 minus 6 over 3, that's negative 8 over 3, all divided by 4, which is the same as negative 8 over 3 times 1/4. And then I guess I'll finish up here because I'm out of space on my page. The 8 and the 4 can interact. This is 2 times 4, so I'll cancel the 4 and I get negative 2/3. Okay, I am going to go grab a better pen and then we'll continue on. Are there any questions on this guy? These are good problems, right? A problem like this may well show up on your test.
Can you walk us through the last steps again, please?
I'm sorry, could you repeat the question? I just couldn't quite hear you.
Could you explain to us the last steps, please? The one where you had a fraction 2 over negative 1/3 and so on.
This step here?
Yes, I feel like I got lost as we were simplifying.
Okay, so here to here, I'm plugging in the things that I found from the graph. Here to here is the simplification, so I assume that that's what you mean, right? So the 2 times negative 1/3, that's the same as 2 over 1 times negative 1 over 3. That's the negative 2 over 3. And then the 3 times 2/3 here, that's 3 over 1 times 2 over 3. So the 3's cancel, and we just get 2 over 1, so that's the minus 2 here. And then downstairs, 2 squared is 4. So that's here to here. And then here to here, I had a common denominator. So I needed to take negative 2/3 and subtract 2 from it. So I write 2 as 6/3. And so negative 2 over 3 minus 6 over 3, that's the negative 8 over 3. That's where this piece came from, and the 4 was just hanging out. And then here to here, I did the whole flip and multiply thing, right? So I want to divide 8/3 by 4. That's the same as multiplying 8/3 by 1/4, and the negative just comes along for the ride. So dividing by 4, same as multiplying by 1/4. Or if you want, you can think of the bottom as 4 over 1, and then I did the flip and multiply thing. And then the last step to simplify here, I just write 8 as 4 times 2, and I can cancel the 4's, so just the 2 remains.
All right, thank you. I couldn't see the last few steps. Thank you.
Okay, yeah, I'm sorry. I know I'm doing something kind of weird here with the camera right now. just for this problem because we have the graph. So I'm going to go grab a pen. I'll be right back. And we can look at some more stuff. Okay. So we also wanted to see 25. That is differentiating theta times cos theta times sine theta. I'm just going to go back to the regular .cam thing now. This is homework 5, problem 25. So on a differentiator, find the derivative of theta times cos theta times sine theta. So my variable here is theta. And this looks like a product. In fact, it looks like a couple of products. It looks like 3 functions all multiplied together. So the question is, oh, my product rule shows me how to differentiate a product of 2 functions. How do I differentiate a product of 3 functions? What do we do when there's another guy? And the answer is you just do it 2 pieces at a time. So the way I'm going to do this, and there is a little bit of choice here. If I want to prime this whole thing, I can treat it like this is F, and this is G. We don't have to split it up like that, but that's one way we can split it up. So theta cos theta, that's F, and sine theta, that's G. So if I follow my product rule, first I differentiate this and I leave this alone, and I'm just going to write that out in the prime notation. So that's theta cos theta primed times sine theta. I leave G alone. And then to that I add what you get when you leave F alone and prime G. So this will be theta cos theta times sine of theta primed. All right, F prime times G plus F times G primed. Now, this piece right here is going to require the product rule all on his own. So if I want to differentiate theta times cos theta, this requires a product. I can think of this as a piece and this as a piece. So I will differentiate theta and leave cos theta alone. So I'm going to write this all out. Theta primed cos theta plus theta times cos theta primed plus over here I have theta cos theta times sine of theta all primed. So that's like the schematic, right? And now each of these pieces we just have to calculate. Remember, theta is your variable. It's like x. The derivative of x is 1. The derivative of theta is 1. So this is 1 times cos theta plus theta times the derivative of cosine is negative sine. So that's negative sine theta. This theta cos theta just coming along for the ride, and the derivative of sine is cosine. Okay. So that's everything, and then we just clean it up as much as we can. 1 times cos theta, well, that's cos theta. Theta times negative sine theta, that's minus theta sine theta. And then plus theta cos theta is plus theta cos squared theta. So this is our derivative here. Yeah, you could take as many things as you want and multiply them together and then calculate the derivative just by splitting it up and doing 2 at a time. So you split into 2 pieces and then apply the product rule. That's our first line there. And then within here, I've got another little product rule. Does this feel a little bit more comfy? Questions on what we're doing here?
I have a question. What happened with our sine theta in the beginning, like at the beginning of the problem? I see where we took the derivative of both theta and cos theta, and then like the sine theta being multiplied by it. What happened to that?
It's still just hanging out, right? Theta cos theta times sine theta. Did I lose him? So, oh, I might have goofed. Yeah, I did. I'm so sorry. Yeah. I'm sorry. Yeah, so most of this is good, but I lost a factor of sine theta. So for the sake of clarity, the derivative of theta cos theta is 1 times cos theta plus theta times negative sine theta. And that was all being multiplied by this guy, who I forgot here. So yeah, that should still have the sine theta. Thank you, Damon. And then this piece is theta cos theta times the derivative of sine is cosine. So that's another cos theta there. Yeah, so I lost this factor here. This guy should have been there. So here's our second little product rule. If I distribute that sign and clean everything up here, we have cos theta sine theta minus theta times sine squared theta plus theta times cos squared theta. Yeah, this is actually looking nicer. And then I can clean this up more because I have a sine squared and a cos squared there. If I factor that theta out.
Hey, Professor, can you move the paper, please?
Yes. So yeah, here's that little inner product rule, and here's the factor of sine theta that I lost when we went through this the first time, and I'm sorry about that. That was my error. Because that sine theta was multiplying the theta cos theta here, it needs to multiply the whole derivative here. That's why I have these big parentheses. And then I distribute this. So sine theta times 1 cos theta, that's sine theta times cos theta. Theta times negative sine theta times sine theta, that's minus theta times sine squared theta. And then this piece is what it was before. It's theta times cos squared theta. Now since that's actually coming out negative, this isn't going to be super nice, but I'll write it like this. Plus theta times cos squared theta minus sine squared theta. And there is an identity we could use on this, cos squared minus sine squared. Does anybody remember what that is?
Is it 1?
If it was
cosine 2 theta.
It's a double angle identity for cosine. That's cosine of 2 theta. Yeah, I think you're fine. So I see a question in chat there. Why is there an extra theta in the first step? Are we asking about this guy? He's coming from the little product rule. Remember, I split the original function up into this piece, which I called f, times this piece, which I called g. So the derivative should be f prime times g plus f times g prime. So this is f prime times g plus f times g prime. So this theta here times cos theta requires a product rule to differentiate, and that's that little product rule that I did inside the big problem. And this theta is coming from the second part of the second product rule. So here I differentiate theta, I leave cos theta alone, plus here I leave theta alone and differentiate cos theta. And the theta over here is coming from this factor, theta cos theta times sine theta, or times sine prime theta. So the derivative of the sine function is cosine, so you get theta times cosine is theta times cos squared. And then each of these terms has a theta in them, so I can factor it out. And what's left is this. And finally, we can use our double angle identity to write cos squared minus sine squared as the cosine of 2 theta. So all together it looks like this. And thank you, Damon, for catching that mistake. I'm sorry about that.
So after the theta you underlined is a negative sine theta.
Yep. Yeah, this is theta times negative sine theta, coming from the derivative of cosine.
Why is it negative?
It's just how the derivative of cosine works out. So the derivative of sine is cosine. The derivative of cosine is negative sine.
Oh, that's right. That's one of the rules you just shared with us.
It is, yeah. It's one of the things that we discovered Monday's lecture, was it? I think maybe even last Friday's lecture we cooked up the derivatives of sine and cosine. So yeah, sine, the derivative of sine is cos. The derivative of cos is negative sine. Let's look at one more like this, because this feels a little bit shaky because I made a mistake there. I want to make sure we're all on the same page and feeling comfy. So I'll give just a second here for anybody who's still writing. Here's my big product rule. Here's my little product rule. But then let's look at something else kind of similar. Okay. Before I wander away from this completely, I want to make a little note. Since we did just learn the chain rule, remember the other double angle identity, the one for sine, says sine of 2 theta is 2 times the sine of theta times the cos of theta, which means 1/2 sine 2 theta is sine theta times cos theta. So the original function, theta cos theta sine theta, could be written as theta times cos theta times sine theta is 1/2 times sine of 2 theta. So my double angle for sine looks like this. If I divide both sides by 2, that gives me this. So my original function, theta times cos theta times sine theta, could be written as theta times 1/2 sine 2 theta. And with that in mind, this derivative isn't too surprising. This is what you would get if you used the product and chain rules to differentiate this. I won't do that to you now, but that's the sort of thing that we'll be looking at next week. So just a little note. What I do want to look at with you now is another kind of double product rule thing. Let's see if we can find f prime where f of x is, let's do x sine x times e to the x. So I need to split this up into two pieces. I know I need the product rule. How about I split this up like this? I'll take the x sine x to be a piece, and I'll take the e to the x to be a piece. So the product rule says my derivative here, I differentiate this and I leave this alone. So that's x sine x all primed times e to the x, I leave him alone, plus, now I leave this alone, and I differentiate this. So derivative of the first times the second plus the first times the derivative of the second. But then this derivative here is going to require a little product rule on its own. Since that whole thing is being multiplied by e to the x, I need to put it in parentheses so I remember to distribute. I differentiate this piece and I leave this piece alone. So that's 1 times the sine of x plus, now I leave this piece alone and I differentiate this piece. So that's x times cosine of x, because the derivative of sine is cosine. All of that is being multiplied by e to the x. And then this piece is x sine x times the derivative of e to the x. Oh, but the derivative of e to the x is just e to the x. Okay, so the same sort of thing going on here. So product within a product. We could distribute, clean up, combine like terms. So I get e to the x sine x plus e to the x times cos x plus, I'll write the e to the x out front here, times x times sine x. And I look for anything I could combine. Nothing obvious. I can factor in e to the x. But really, yeah, we just leave it like this. This is good. So products within products, products within quotients, power rule things within product rule, all of these can happen. I'm not going to beat you to death with them. The goal here is to get you comfortable. So, so I'll leave it at this for these guys. I do see Zach has a couple problems requested. There are a few other problems that were asked for earlier, so I'm going to start going through them in order. 22 and 32 from homework 5, and then 5 and 7 from the study guide. Let's take a look at 22 from homework 5. Oh, we already did 22. Yeah. So if you didn't get to see 22, just rewatch the start of the video. We also wanted to see 32. All right. Ah, yeah, 32 is fun. We want to find the 114th derivative. That's what that notation is. So this notation, the d114 over dx to the 114, this is the same as saying this. So dn over dx to the n, that's the nth derivative of f of x, which is the thing when we talked about higher derivatives, the notation I used was this. So for example, like d2 over dx squared of f of x, this would be f prime prime, right? So just the notation there is perhaps a little bit confusing. So in other words, what I want to do is differentiate the sine function 114 times. Let me rephrase that. What I want to do is find the 114th derivative of sine. I don't want to differentiate it 114 times. I will get tired, probably around the 4th or 5th time. But let's go ahead and differentiate 4 or 5 times and see if we can notice a pattern. So we want the 114th derivative of f of x equals sine x. Okay, well, the first derivative of sine is cosine. The second derivative is what you get by differentiating the first derivative. So you just differentiate again. Derivative of cosine is negative sine x. And you might start to smell some pattern here even right away. The third derivative is the derivative of the second derivative. So I just differentiate this again. The negative comes along for the ride, and the derivative of sine is cosine. The fourth derivative, and this is where I'll switch to this other notation, I differentiate this again. The negative comes along for the ride, and then the derivative of cosine is negative sine. And the negatives undo each other, we just get sine x. The fifth derivative, if you think about it, the fifth derivative is going to be the same as the first derivative because I'm just differentiating, this is my original function coming back. So the fifth derivative is cosine. And that's your pattern. Has anybody ever seen a pattern like this before? Not necessarily involving derivatives, but just a pattern where every 4 terms, something repeats. I know some of you took pre-calc with me, and I know we talked about this, but it was one of those days where we had a little bit of extra time to talk about something fun. Powers of I, the imaginary number I, also cycle like this. I to the 0 is 1, I to the 1 is I squared is -1, I cubed is -I, and I to the 4 is 1 again. So you cycle every 4, and there is a deep connection there that I'll be able to show you at the end of Calc 2. But for the purposes of our problem, what we notice, if you don't differentiate at all, you've got sine. If you differentiate once, you've got cosine. If you differentiate twice, you get negative sine. 3 times, negative cosine. 4 times, you're back to sine. So every 4 derivatives, you start over. It's a cycle. So what we want to do is ask, if I were to go 114 times, how many times do I go through that cycle? In other words, if you've heard of modular arithmetic before, I want to know what is 114 mod 4, or how do I split 114 up as a multiple of 4 plus some remainder? 100 is divisible by 4. 12 is divisible by 4, so 112 is divisible by 4. So I would split 114 up as 112 plus 2, like this. And 112 is divisible by 4. If I differentiate the sine function 112 times, what will I get and why?
You'll get sine x.
Right. I don't know. What is 112 divided by 4? Arithmetic sucks. 28. So this is... Okay. So because 112 is a multiple of 4, the first 112 derivatives land you back home at sine. Then you differentiate 2 more times. So in other words, the 114th derivative is the same as the second derivative. And the second derivative I have right here is negative sine. So that's it. This is a lot like those problems where I ask you for the 250th power of I. If you remember those silly problems from pre-calc or algebra. It's not too bad because the powers cycle. Here, it's not too bad because the derivatives cycle. So you just have to figure out where in that cycle you land if you run through it, if you differentiate 114 times. Since the cycle is of length 4, every 4 derivatives take you back to your starting point. So I take 114 and I write it as a multiple of 4 plus something else. In other words, I pull out all the multiples of 4 that I can from 114. There were 28 multiples of 4 in there. So we run through that cycle 28 times and then take 2 more steps. So here's that cycle. We run through it 28 times and then take 2 more steps, right? Differentiating twice. And that gets us back here. So the 112th derivative of sine is sine. The 113th derivative of sine is negative cosine. The 114th derivative of sine is negative sine. Cool stuff, right? Questions on this problem? Okay, so I'm going to keep going in order. 5 and 7 from the study guide. And then we also want to look at 31 from homework 5. 31 from homework 5 is right next door. Yeah, we will come back and do this limit. That's a good problem to practice. But first, let's bounce over to the study guide for a second. This is Calc 1. We wanted to see which number. 5 and 7. Okay. Sure. Yeah, 5 and 7 are kind of similar. They're both limits at infinity. The trick for 5 is an algebra trick. The trick for 7, you could also think of that as a little algebra trick. So remember what we want to do for all these limits at infinity is find what is like the dominant.
Excuse me, sir.
Yes.
Yeah, question number 2 about gas study. So how to describe this on the paper? Because it's only the graphs.
So for for these guys where you're calculating a limit just based on the graph, you're asking specifically about number 2, right?
Yeah, number 2.
Don't stress too much about showing a lot of work. Just on your paper, draw for me any graph that has these features. So if you want to, you can sketch a graph that looks like the one you picked. Or if you want to draw your own graph on paper that has these features, a removable discontinuity at 1 and a jump at 3, that would be fine. So yeah, you just, if you're asking like, how do you show work or what kind of work am I expecting you to show on this, just draw for me any graph that has these features. If you want to, you can sketch the one that they give you here that you pick, or you can draw your own. Yeah, either would be fine.
All right, thank you.
Yeah, of course. Okay, and the limit we wanted here, square root of x plus 3x squared over 2x minus 1. So let me switch you back to the dot cam. This is what we want. So what I was saying, the trick here is to find like the dominant term. We want to know in this race to infinity, who wins? What's the fastest growing piece anywhere in this function? The fastest growing piece downstairs is definitely the 2x piece, or the x piece, this one. The fastest growing term upstairs is the 3x squared piece, or just the x squared piece, but he's under a square root. So the x squared under the square root only grows as fast as x. So what I'm going to do here is divide top and bottom by x, or multiply top and bottom by 1 over x. Because that will kind of normalize those fast-growing terms. Downstairs, the algebra is straightforward, but upstairs, it's a little bit tricky. Because in order to get this 1 over x to interact with this stuff, I need to write it as the square root of something. So downstairs, I just distribute. I get 2 minus 1 over x. Upstairs, in order to get this and this to play together, I have to treat it as the square root of something. And 1 over x I can treat as the square root of 1 over x squared. Since we're sending x to positive infinity here, I don't have to worry about absolute values or any weird business like that. And now that I have a square root times another square root, I can write that as 1 square root with the product of the insides. So this is, the top is now 1 big square root, and inside it is x plus 3x squared times 1 over x squared. And my downstairs is what it is. So this is the sneaky algebra trick that's necessary for limits like these. Now that my 1 over x squared is inside the square root like that, I can distribute it. 1 over x squared times x is 1 over x. 1 over x squared times 3x squared is 3. And now I can take my limit. As x goes to infinity, 1 over x goes to 0. So this is upstairs, the square root of 0 plus 3. And downstairs, I have 2 minus 0. So that's the square root of 3 over 2. This trick is not an uncommon.
And we have to show all that.
I'm sorry?
Sorry.
No, no, it's okay.
You do want to see all that work, even though when we look at it, we can tell what it is.
I need to see enough work to show me that you know that this is the game. If you wanted to go from like here to, I don't know, here to here or something like that, that would be okay. But I definitely encourage you to write out all the steps. At least if you're not going to do it like as a matter of habit on the homework, if you've done enough of these that they all feel easy, when it comes to the exam, humor me a little bit and make sure you show enough work so that I can be like, oh yeah, this person definitely knows what they're doing. They're not just writing down an answer from Wolfram Alpha or something.
Okay, thank you.
Yeah, of course. Other questions on this one? Okay, there was another study guide problem there that we wanted to see, so let's take a look at that. Five and 7. Yeah, so 7 is similar. Again, we're taking a limit at infinity, and again, the top and bottom both run off to infinity on their own. So in order to sort this out, we need to do some sort of normalization. Write this down, and then I'll switch back to the dot cam. Okay. So just like in the previous problem, I want to ask, what is the dominant term? What's the fastest growing term upstairs, fastest growing term downstairs, fastest growing term overall? So I can try to divide out by it and normalize the function so that I can take the limit. Definitely the only thing that grows here is e to the x. And e to the x does grow very quickly. So that is the dominant term upstairs and downstairs. So I want to divide top and bottom by e to the x. Remember that fractions are grouping symbols, so we've got parens here like these. So in other words, we need to distribute the e to the x. So I'll have 7 over e to the x minus 1 divided by 7 over e to the x plus 2. Now as x goes to infinity, e to the x himself goes where? So I'm coming off to the side here to do a little bit of side work. What is the limit as x goes to infinity of e to the x? It's infinity. Yeah, look at the graph. So as x goes to negative infinity, e to the x goes to 0. As x goes to positive infinity, e to the x goes to positive infinity. Right, so if I wander off to the right, this thing just gets bigger and bigger and bigger and bigger. Oh, sorry, blowing up to infinity. As you wander way off to the right, you go to plus infinity. As you wander way off to the left, you go to 0. So this piece, this is infinity. You can think of it as e to the infinity, and e to the infinity is infinity, right? You take e and you raise it to a really, really, really big number, you're going to get out a really, really, really big number. What this means is that 1 over e to the x is going to go to 1 over infinity, and that's 0. 1 divided by a really, really, really big number is a really, really, really small number. So each of these pieces is going to 0. If you wanted to write it out nicely, I think the easiest way to write this so that anybody would understand it is probably going to be like this. And then if you take a medium-sized number like 7 and you divide by infinity, you get 0. So that's 0 minus 1 over 0 plus 2, which is negative 1/2. Difference between infinite and plus minus infinite. Well, positive infinity you can think of as just being a huge positive number, and negative infinity you can think of as being a huge negative number. That's the intuition that I recommend. So remember, think about plus infinity as a huge positive number, and negative infinity as a huge negative number. So we shouldn't ever get both plus and minus infinity out as the limit of one particular function. Your function is either going to plus infinity or to minus infinity as x goes to plus infinity or minus infinity, if it has any end behavior like that at all. If you look at something like 1 over x, as x goes to 0, on the right-hand side, that goes to plus infinity. On the left-hand side, that goes to minus infinity. So the left and right limits there disagree, so we would say that's a DNE. So if you're taking a limit at some finite number, like the limit as x goes to 0 of 1 over x, if on one side you go to plus infinity, on the other side you go to minus infinity, that's a DNE, because the left and right limits are not the same. So I'm sorry, just addressing a question in chat there. Yeah, so Zach asked, the best way to start these problems seems to be multiplying by 1 over x, or 1 over x squared, or 1 over e to the x. The general philosophy here is to divide out by the fastest growing term. So e to the x is the fastest growing term in the original function. So I want to divide out top and bottom by e to the x, which is the same as multiplying by 1 over e to the x. So yeah, Zach, what you said is correct. Identify the fastest growing term, whatever that is, and then multiply by his reciprocal on the top and the bottom. And then sometimes you'll need to do various flavors of algebra tricks in order to get the pieces to talk to each other. But that is the strategy, yeah.
Question.
Yeah.
So what we're really trying to do is we're actually trying to slow down the function just enough to try to take a point.
Mm-hmm. That's the idea. Yeah, we want to slow down the function's growth upstairs and downstairs enough so that we can see what its finite end behavior is. Let's look at the graph of this guy. So here's the numerator all on his own. And you see as x goes out to plus infinity here, this guy's diving off to negative infinity. He's diving off to negative infinity really fast. That's this. As you put in bigger and bigger x values, this piece takes over. And he wants to run off to infinity. So 7 minus him wants to run off to negative infinity. So on his own, this piece is uncontrollable. It explodes to negative infinity. The bottom, all on its own, would do something similar. If I graphed, if I graphed the bottom all on its own, let's maybe do that before we look at the ratio. He wants to go up to positive infinity. So the top wants to go to negative infinity. The bottom wants to go to positive infinity. They're fighting each other. And in order to see who wins the fight, I want to divide out by those pieces that are making it explode. And those pieces are the e to the x pieces. So here's what the overall function looks like. And in order to find this limit as x goes to positive infinity, I had to divide top and bottom by e to the x. And we found this guy. this horizontal asymptote here. Now notice as x goes to negative infinity out here on the other side, something else is happening. How could I find that other horizontal asymptote? I claim it.
You flip it.
Say that one more time.
You just like make it positive.
So it's actually not positive 1/2. This guy is actually positive 1.
I see, I see.
So it's not quite that simple. Any other conjectures?
Add the slope by 2.
Well, so the green line we found by taking the limit as x goes to positive infinity, because as we wander out further and further to the right, this function is settling down on that green line. This function settles down on this purple line as we wander off to the left. So if I want to find that guy, I should take the limit as x goes to negative infinity. So remember, horizontal asymptotes are limits at infinity and negative infinity. And some functions have different asymptotes on the left than they do on the right. To find the other horizontal asymptote, calculate lim x to negative infinity, 7 minus e to the x over 7 plus 2e to the x. As x goes to negative infinity, e to the x goes to 0. So this is 7 minus 0 over 7 plus 2 times 0, which is 7 over 7 is positive 1. So this section, limits at infinity, we covered it fairly quickly as section 2.6. You may want to go back and remind yourself some of the rules that we learned there. So this trick of dividing top and bottom by the fastest growing term, it's a good trick, it works. But in order to solve these problems quickly and in order to have a good intuition for them, you may want to go back and reread that section in the textbook. Remember?
Question.
Yeah.
So to find the positive slope, how come we didn't try to divide by the fastest growing term like we did at the first one?
Oh, I didn't have to, because as x goes to negative infinity, nothing here is blowing up. As x goes to negative infinity, these pieces each go to 0. So the reason we had to divide top and bottom by that e to the x, remember, is because this piece was going to infinity. This piece was going to infinity. Like you said, we had to slow it down so we could see what was going on. As we send x off to negative infinity, these guys don't need to be slowed down because e to the x goes to 0 as x goes to negative infinity. So let me pull up the textbook 2.6 and I'll show you what I mean by going back and taking a look at some of these things. There are some things there that you definitely do want to remember. And some of them are exactly what we're talking about right now. So limits at infinity, the connection to horizontal asymptotes, right? So remember, horizontal asymptotes, these things, can be found by taking the limit at plus infinity or the limit at minus infinity. And they can be different, like here at arctan. This was one of our special limits that we want to remember, right? Arctan goes to negative pi over 2 if you wander off towards negative infinity, and positive pi over 2 if you wander off towards positive infinity. And there are a couple other limits in here that they talk about, right? So we had this theorem that 1 over any positive power of x will go to 0 as x goes to infinity. And also 1 over any positive power of x will go to 0 as x goes to negative infinity, provided this thing is defined, meaning it's not like a square root. But there are a couple other limits in here that you will want to hold on to, namely the exponential stuff. Yeah. So the limit as x goes to negative infinity of e to the x is 0. And the limit as x goes to positive infinity of e to the x, it's not written here, is positive infinity. So every blue box statement in section 2.6, you really want to remember. In general, any blue box statement anywhere in the textbook, you really want to remember. But especially here, there is kind of a memorization vibe, because it's not the sort of thing that we cook up from first principles. It's something that we get from graphs or by thinking about a function carefully. Don't stress about this. But all the other blue box statements here in section 2.6, you will want to go back and revisit them and make sure you know them. So here, let me just for everybody's sake, let me go ahead and write those things down. Some important things to remember. Some important stuff from section 2.6, some important limits to remember. What other things did we have? These were the big ones. And then we also had the definition of a horizontal asymptote. So we've covered quite a bit, and I think it's possible for this particular stuff to get lost in the wash, because the limit laws, we use those all the time. The derivative rules, we use those all the time. But these things we kind of just did in section 2.6, and we haven't really used them anywhere since. So you might want to write these down and try to sort of refresh yourself. Tanzina in chat asked, do I want you to email the study guide stuff to me? If you want to talk about a problem, if there's a problem in the study guide that you're concerned about or you want to talk about just to make sure that we're on the same page, you can email that to me. But to turn it in, make sure you follow the directions on Canvas. To turn in the study guide, and in order to get credit for it, I need you to submit it under the assignment titled SG1 in Canvas. So once your study guide is all done, you've got all your solutions written out, scan them, and then submit them on Canvas under the assignment SG1. But I do want you to talk to me about your study guide. I would really like to be able to see some of your work and give you some notation advice before the exam. And the best way to do that is either by coming to an office hour or, yeah, emailing me a picture or a scan of it. So for discussion, emailing a picture is fine. For handing it in, make sure you scan it and submit it on Canvas. So Tamji, I'm glad that you discovered that issue with HonorLock. Send me an email about it, and we'll start figuring it out. We do need to get you in there and get that working. If necessary, there are some laptops at the college that are set up and definitely are able to run HonorLock that I've been told I can get to loan out for you guys. So if for whatever reason, like you don't have a webcam or there's some software issue with your computer, it doesn't want to run HonorLock, let me know as soon as possible, and we can try to get you one of those loaner laptops for our test. All right, what else would we like to do? I think we got a little bit more time left here today. Oh no, actually we are right out of time. So I have to, oh no, we're gonna go a little bit later. Okay, so Tomji, if you could send me an email reminding me of that, and I will send that off to my department chair, and we should be able to get you one. You may need to come to campus to pick it up, but send me an email or a Canvas message about it, and we'll get that figured out today, I promise. All right, yeah, so we are gonna go a little bit over because I started a little bit late. I see there's one other question we wanted to look at there, number 31. And I guess that's probably in homework 5. Oh yeah, we talked about it, but we didn't actually do it, right? Yeah, so let's come back here and actually get this guy knocked out. Oh, that's Calc 2, sorry. Okay, yeah, good stuff. Thank you for the reminder. Okay. So the trick for this guy is we need to lean on those 2 special trig limits we have. So we know that the limit as x goes to 0 of sine x over x, that's 1. And we know the limit as x goes to 0 of cos x minus 1 over x is 0. So those are our 2 special limits from section 3.2. In order to evaluate the limit in problem 31, I'm going to split it into 2 things, each of which I can kind of treat like these. So I'll show you what I mean. First, I'm going to split that fraction up like this. And then I'm going to multiply by theta over theta. So I've got these 3 fractions all being multiplied. This theta I'm going to give to this guy, and this theta I'm going to give to this guy. So what we get is lim theta to 0 cos 2 theta minus 1 over theta times, times theta over sine 5 theta. You see it, if I multiplied these 2 fractions together, I will get my original. The thetas would cancel, and I'd have this over this. In order to make use of these special limits, though, like the sine x over x limit, remember when we did an example like this the other day, we had to make sure the inside of the sine function is the same as the x downstairs. This is the reciprocal of something that looks a lot like that, but the top is missing the 5. So him, I'm going to multiply by 5 over 5. And this guy, same sort of thing. I need the bottom to look like the inside of the cosine. So he's going to get multiplied by 2 over 2. And then just like I grouped the thetas, I'm going to group the constants. So here I'll have cos 2 theta minus 1 over 2 theta times, I'll leave the 2 from the top outside. And then this other piece, I'll write him with his own limit, lim theta to 0, 5 theta over the sine of 5 theta, and then the 5 from the downstairs, he's going to have to stay out. Each of these pieces now looks like one of those special limits. This guy is actually the reciprocal of something that looks a lot like that. So a consequence of this, since lim x to 0 sine x over x equals 1, you can take reciprocals everywhere, and you'll find that lim x to 0 x over sine x, that's also 1. If you flip this over, you flip this over. Since 1 over 1 is 1, x over sine x and sine x over x both have limit 1 as x goes to 0. In other words, this piece right here is 1. Similarly, this piece right here is 0. So what I get from my limit is 0 times 2, that's the first piece, times 1 times 1/5. But that's 0 times 1/5, which is 0. Right? So I take my fraction, I split it up like this, and I give the constants needed to make the things look like the special limits. One consequence of this special limit is this. This piece looks like x over sine x as x goes to 0, so this piece will go to 1. This piece looks like cos x minus 1 over x as x goes to 0, so he's going to go to 0. But the juggling of the constants is nice. In particular, it's good that we're able to see that this piece here would go to 1/5. So this is a nice sneaky problem that involves both of those special trig limits. There is more stuff like this in the book around that section. If you go to section 3.2 in the textbook, you can find more problems like this to practice, and I would encourage doing it. I think also homework 5 has at least one more of these, I believe.
Quick question.
Yeah.
Cosine of 2 theta minus 1 over 2 theta. Remind me how that equals 0?
Say that again. How do we know that that equals 0?
Yes, sir.
Because cos x minus 1 over x goes to 0, and here we could substitute x equals 2 theta. So lim theta to 0 cos 2 theta minus 1 over 2 theta. If we substitute x equals 2 theta, then as theta goes to 0, x goes to 0. So that limit is the same as the limit as x goes to 0 cos x minus 1 over x. And this is one of our special trig limits. We know that that limit is 0. If you want to kind of jog your memory, why is this limit 0? Why is that special trig limit the way it is? Then you could go back to the video from, I think, last Friday. The trick was to multiply by cos x plus 1 over cos x plus 1, and then we're able to turn it into some stuff involving the sine x over x limit. But yeah, those two limits in the recall box at the top, those are two good ones to commit to memory.
Thank you so much.
On the 2.6 thing, because it's not from 2.6, but yeah, those are definitely two special limits that you want to remember, just like the limits at infinity that we talked about. Other stuff? Anybody else got any other questions on this one? Anything else we're wondering, or comments, or anything like that? Yeah, no problem. Okay, then I'm going to go ahead and end our meeting here for today. Remember, Friday is the exam, so we're not going to have a normal class meeting. Instead of a normal class meeting at 9:45 on Friday, you're going to go to Canvas. You're going to click on the Honor Lock link on the left. You're going to click Launch Proctoring next to Exam 1, just like for the practice quiz. If you haven't done the practice quiz yet, please do it. And also make sure you read the instructions that I posted in that Canvas announcement, how to take Exam 1, how to hand in Study Guide 1. That stuff's very important. You need to follow those directions exactly. If you anticipate running into any technical issues, please let me know. If the practice quiz doesn't work well, or if you know that you need some hardware or something for whatever reason isn't working, talk to me. The college does have loaner laptops, but we need to get that checked out and get that to you like immediately if you need one, because the test is going to be on Friday. I'll have a 2-hour window open where you can take the test. So from 9:45 to 11:45, the test will be open. And you'll have 75 minutes on the test itself. So whenever you start the test, you'll have 75 minutes to finish it, and you can start it anywhere in that 2-hour window. But the test will close and won't be available after 11:45. So make sure you start at least 75 minutes before 11:45. That is it. So if you got any stuff you want to talk about, problems, you want me to look over your study guide with you, remember I strongly encourage you to do that, at least with a problem or two. Come see me in office hours today. If you emailed me about scheduling an extra office hour, I should have gotten back with you. If I haven't, then I'll do that as the day progresses. So come see me in office hours, 1 to 2, and that's it. I'll see you guys either there or in class on Monday. If you have any questions on Friday, remember you can reach out to me via a Canvas message. I'll be watching those really carefully to try and keep everything under control. But read the instructions on Canvas first. All right. Okay. I wish you guys lots of luck on the test if I don't see you in office hours this afternoon. And that is it. I'll see y'all later.